Okay, now let's look at how the measurements will be done. Okay, I've turned things around so you can see the picoammeter and measure the current. And you can also see the computer display showing the program that we're using to set the voltage at the cathode. Right now, the voltage is set to 0. And you can see that the current is minus 3.8 or 3.9 nanoamps. That's a small current, but this meter has no problem measuring it. That's its job. Something you should think about for a minute. Why is the current negative? Remember, this is the current that flows from the anode, from the cathode, the photocathode, to the anode in the circuit, and then continues along to this box. So you should make sure you understand why that current should have a negative sign in front of it. Here, let's see how the magnitude of the current changes when we change the voltage applied to the cathode. We can change the voltage in either direction, to positive or negative. Let's see what happens when we go to positive. When we go to positive voltages, the current gets smaller and smaller in magnitude. And eventually, the photocurrent we expect is going to go to 0. The actual measurement switches sign, something we'll want to investigate in a second, but definitely much smaller than we saw at 0. Interestingly, if we go in the other direction, if we make the cathode voltage negative with respect to the anode, the current gets larger and larger. It doesn't continue to get larger and larger without limit. Eventually it saturates. Oops, let me just change scales here so you can see that. Here at about 25 nanoamps. Now, we're primarily interested in what happens when the cathode voltage becomes positive, but it's also worth thinking about why does the current get larger and larger when we make the cathode negatively charged with respect to the anode? That is, why do we collect more and more of the photoelectrons under this situation compared to this situation? And of course, why do we collect a smaller and smaller fraction when we make the cathode positively charged with respect to the anode? Okay, let's go back down here. Great. Now, the main goal of the experiment is for each wavelength to find the voltage at which the photocurrent goes to 0. It seems like an obvious job now. What we would do is simply make adjustments until the magnitude of the current went to 0 here. And that's interesting. It actually goes to 0 and then it changes sign, somewhere close to here. Now we're going to do something like that, but I think it's worth letting you see that this is not exactly the job that we need to do. For example, if we find this condition, let me look a little more carefully here. Oh, that's not what we wanted. Okay, just about there. You'll see that there's something funny going on because the current has changed sign, and we don't have an obvious explanation for why the current should ever change sign. Let me show you something else. If I block the light now, then naively we'd expect we block all of the photocurrent. But that's not what happens at all. Now we get a much larger positive signal. So this is a little experimental complication. It's only important to let you realize that there are always experimental complications. We have to find out a way around them. What's going on is that the impedance of the phototube is apparently not infinity. When we apply a voltage across it, a small dark current will flow, even if there's no light falling on the phototube. And we have to take that into account when we do our measurements. It's not hard to do. All we have to do is realize what we want is not to get 0 on this meter. what we want is zero photocurrent. And that would be the condition where the reading on the meter does not change even when we block the light. Okay? So for example, at this point, the reading on the meter becomes more positive when we block the light, which means there's still a contribution from photocurrent that is a negative current. If we go to this point, 1 volt, when we block the light, we see something else. We see the positive current get very slightly smaller when we block the light, but it's only a slight change. That means that the contribution of the photocurrent is very small. We're much closer to the true zero than we were before. If we were to go to minus 2 volts, I'm sorry, 2 volts applied to the photocathode, we'd see that when we block it, the change is actually in the opposite direction now. So we've gone too far. So the true voltage is in between 1 volt and 2 volts, someplace. And we find it by finding the point, the cathode voltage at which this number doesn't change when we block the light from the mercury arc lamp. I won't go through that now. That's the actual experiment. I'm just showing you how the experiment works here. But I wanted you to get this subtle point. It's just a subtle point. If we had perfect equipment, we wouldn't have to do this last step. But because we don't, we do. Just to wrap up then, in our experiment, what we would do is find the stopping voltage for each wavelength of light. We would go to different wavelengths of light by using the diffraction grating to break up the light into different wavelengths, so that only one wavelength is passed to the phototube at a time, and then using the appropriate filter just to clean up the light to make sure that there's no stray light that's at the wrong frequency that's entering the phototube. All right, and that's the photoelectric experiment. Let's stop here.